Alright guys, so as you can see today, a little Star Wars theme to get you going. We are going to be talking about the story of numbers. So in a math class far, far away, how did numbers begin? Alright, so way back, when we were still, cave dwellers, hunter and gatherers, and we were looking for food and very basic, if you would, kind of cavemen, if you would think. So let's imagine we have a caveman, and his name could be a rock. Now, back in those times, in order to marry someone, you actually needed to show strength and show power. So he needs to know how many mammoths he needs to kill to marry the love of his life. So what type of numbers do you think began to be used first? If we look at the world, we start to see numbers that exist in real life. 1 mammoth, 2 mammoths, 3 mammoths, etc. Okay? And we're actually going to call those natural numbers. Some people actually call them counting numbers, but natural numbers is what we tend to call them in the math world because they appear in the natural world. So any number from 1 until as high as you can count infinity, okay, those are natural numbers. Okay, but we actually come to a point in our lives where we need to symbolize nothing. What if a rog was really terrible and he could never take down a mammoth? What symbol would denote nothing? So, in 628 AD, so there's a long gap between natural numbers and the first appearance of 0. But by a guy by the name of Brahmagupta was the first to write about the number 0. So if we put 0 with the natural numbers, we create a new set of numbers. Those numbers are actually called whole numbers. Then there comes a point in our lives where we need to figure out negative numbers. If you borrow money from me, how am I going to show how much money you owe? If the temperature drops below 0 degrees, how do I show that? As we're developing things, we start to realize that the freezing point of certain chemicals is much lower than 0 degrees Celsius or even 0 degrees Fahrenheit. How do we show this mathematically? So we need to keep a record of debts owed and transactions as well as temperatures that drop well below freezing. So believe it or not, there's actually a guy named George Cantor, and at the age of 22, he actually came up with what we know as negative numbers. When we combine the negative numbers with the whole numbers, we actually get the set of integers. So all the negative numbers, all the positive numbers, and 0 is the set of all integers. So do you see that we're beginning to develop a larger set of numbers? We have more and more numbers in our repertoire to use. So we have negatives, positives, and zeros, but what happens if I need something in between? What if you owe me $1.50? Or what if I'm cooking and I want to know I only need a half a cup of milk? How do I count a half and how do I count a third? So these numbers are actually fractions, and if we add fractions to the set of integers that we have developed, we are actually going to get rational numbers. And you won't believe this, but George Cantor actually included fractions in his paper. So not only did he make negative numbers, but he also talked about fractions. Pretty smart guy for being 22, if I'd say. So, you may think, that's it, right? That's all the numbers we have. There's actually one more set of numbers. We go a little bit deeper and we come across problems like pi. How do we write pi? We can't write it as a fraction because it never ends. 3.14159 ... How do we end the decimal? Well, we can't. That means we can't write it as a fraction. If it goes on forever, it's an irrational number. So irrational numbers can still be put on the real number line, but they can't be written as fractions. So they're not rational or irrational, okay? So you're probably wondering, what does this have to do with me, Miss Norton? Well, here's what we've got. If we take all the numbers and put them together, we create different sets. And if you look at this right here, this whole big oval is the real number system. So we have been talking about complex numbers that are imaginary. Notice that complex numbers and i's will never appear in this because they're not real. So we are taking all of these real numbers and just breaking them down. So you see how we had the natural numbers. By adding 0, we became whole. By adding negative numbers, we became the set of integers. And by adding fractions, we became the rational set of numbers. However, all the way over here by itself is irrational. Things like the square root of 2, things like pi, because these never end and they cannot be written as fractions. So irrational is still real, it's just not rational. So as I've been saying before, rational numbers are numbers that can be written as a fraction. So you have several options. Now, it says ratio. Just remember that ratio is another word for fraction. Okay? So when written as a decimal, they end or they repeat. So in the example of 0.6666666 repeating, that would be your 2/3. See, because it can be written as a decimal. Anytime the numbers repeat, it is rational. So for example, 1/3 is 0.333333 repeating, therefore it is still rational. Okay? If I get something like 0.2867 and then it repeats over and over, for example, like 2867, 2867, 2867, and it keeps repeating over and over and over, that is still a rational number, because it repeats over and over and over and over again. Now, if I have a decimal like 0.472193, and that's it, it ends. That's it. That is actually a rational number. Because it ends, I can write it as a fraction, and I can change this and move the decimal over and put it over, let's see, 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, oops. 3, 4, 5, 6. So I converted this decimal that terminated or ended and into a fraction. So because any decimal that ends can be converted into a fraction, it's a rational number. Now if we take a look at these numbers here, square root of 3, pi, and square root of 5 over 2, they don't end and they don't repeat. So they are what we call irrational numbers. Now, even though we don't use irrational numbers in the real world a lot, we use pi a lot as far as circles go, but we don't actually see them when we're transacting with money. You don't say, well, you owe me pi. Okay, pi dollars, what, you know? So we don't, but they still exist on the number line. So you can see that pi is just a little bit greater than 3. Square root of 17, that while it's irrational, is still a little bit more than 4. Okay? Alright, so here we have a subset of numbers, 5, 1/2, 0, square root of 2, negative square root of 2, and pi. So we have a mixture of rational numbers and a mixture of irrational numbers, and we want to know, is it closed under the set of addition? What that means is, a set of numbers is closed if when I add these two numbers, I make another number in the subset. If I add 5 and 0, I get 5. So 5 is already a piece of this subset, so it's closed. You have to actually check for every single addition problem. So let's say, for example, I want the set of all even numbers. So I'm not going to write them all because they go forever, because it's an infinite number of even numbers. So if I said 0 plus 2, I get 2. 2 exists is an even number, so we are good. 0 plus 4, 0 plus 6, 0 plus 8 all create numbers that are already in my set. Now if I do 2 plus 2, I get 4. And 4 is in my set, so I'm okay. 2 plus 6 is 8. It's even, so we're good. 2 plus 8 is 10. Now, while I don't have 10 showing, we know this is the set of all even numbers, so 10 would be the next number that appears. We are good. So you keep checking all of these, and you'll notice that anytime I add two even numbers, I will result in an even answer. So what this means is that this set of all even numbers is closed under addition. So that was easier, but now we need to take a look at these 6 numbers that I gave you, 3 rational and 3 irrational. So what you see here is we've actually created a table of all the possible additions that can be done. 5 plus 5 is 10, 5 plus 1/2 is 5 1/2, 5 plus 0 is 5, 5 plus the square root of 2, 5 plus the square root of 2, 5 minus the square root of 2, and 5 plus pi. Now here's a problem. If I take a look at my answers, 5.5, 5.5 is not one of these 6 numbers in that set. That one thing alone means that this set is not closed under addition. Because I can create a number by adding that's not currently in my set, which means there's some other numbers out there that need to come into my set in order to be closed. Now, it doesn't just have to be addition. It can be multiplication. So let's use the same set of numbers, and we can do and check their multiplication to see if they're closed. Before we do the chart, let's do an example. Let's say that I have -1, 0, and 1 as my set, and I want to know, is it closed under multiplication? So I would do -1 times -1, I would do -1 times 0, -1 times 1, then we have 0 times 0, 0 times 1, and 1 times 1. So these are all the possible multiplications that can occur with these 3 numbers. So -1 times -1 is 1. 1 is a member of my set, so we're good. -1 times 0 is 0. 0 is a member of my set, so we're still good. -1 times 1 is -1. -1 is a member of my set, so I'm still good. We are looking for a number that is not in my set. If that number appears, then it's not closed. So 0 times 0 is 0. 0 is a part of my set. 0 times 1 is 0. 0 is a part of my set. And 1 times 1 is 1. 1 is a part of my set. So because of all of the multiplications resulted in a number that is already included, this set is closed under multiplication. Alright, so here are all the possible. There are 36 different multiplications that can occur with that set, 5, 1/2, 0, square root of 2, 1 over square root of 2, and pi. You'll notice that they've already started the table for you. 5 times 5 results in 25. I can go ahead and stop and not do the rest of the chart because 25 is a number that is not a part of my set. That means that this set of numbers, 5, 1/2, 0, square root of 2, and 1 over square root of 2, and pi are not closed under multiplication. So for these 6 statements, we want to say always, sometimes, or never true. So the sum of a rational number and a rational number is rational, and that is always true. So that means that if I have a set of all rational numbers, it will be closed under addition. The sum of a rational number and an irrational number is irrational. That is always going to be true. The sum of an irrational number and an irrational number is irrational. Now we have sometimes, because look, if I were to take square root of 2 and add a negative square root of 2, I result in 0, and 0 is rational. 5 and 6 are sometimes as well. 0 times pi is 0. 0 times any irrational number is going to be 0. Alright, well that's it we have for today. Bring your questions tomorrow. I'll see ya.